Today we will be learning about exponential equations and how to solve this kind of equations. Let's define first what are exponential equations. Exponential equations are equation with variables in the exponents. So we are looking for the missing variables, and these variables are located in the exponents. So this could be in the form a to the x is equal to b to the y, where a and b are elements of real number, but later on you will know what are the restrictions of these values. But in this session, we will be focusing on exponential equations with the same base. So which means that I'm actually talking about a to the x is equal to a to the y. And to solve this kind of equation, we have to know the property of equality of exponential equations, which means that if you have a to the x equal to a to the y with a equal to each other, so they have or they are of the same base, then therefore it implies that you can equate the value of x equal to y. So we're not necessarily canceling out the value of a. What we're talking about here is to one-to-one property. That means if the bases are equal, then therefore the exponents are equal. Okay, let's begin with some examples. Okay, the first example is 2 to the x equal to 16. So what will be the value of x that will result 16? To have a result equal to 16. So we mentally compute this one, and we can say that x is equal to 4. Okay, because 2 times 2 times 2 times 2, you multiply 2 by itself 4 times, it will give you 16. But how can we show algebraic solution for this one? So the first thing that you're going to do is to remember that a to the x is equal to a to the y. So our target is to have the same base. Okay, and in order to form these two expressions in both sides in the same base, we have to transform the standard form of the number 16 into base 2. So therefore, we can rename 16 as 2 to the 4, because 16 is 2 times 2. 16 is equal to 2 times 2 times 2 times 2. Since we have already the same base 2 and 2, then therefore we can equate it. This implies that x is equal to 4. Okay, and to check whether your answer is correct, then you can replace 4 to the value of x in your original equation. So 2 to the 4 is equal to 16. Okay, let's try other examples. Let's have 3 to the power of a minus 7 equal to 27 to the power of 2a. Okay, as you observe, we have two different bases here. We have base 3 and base 27. And of course, we can simplify 27, or we can transform 27 in terms of base 3, because 27 is 3 times 3 times 3, which is definitely equal to 3 cubed. So that means 3a to the 7, a minus 7, is equal to 3 cubed to the power of 2a. Okay, so we have already expressed 27 in base 3. So what are we going to do next? The next part is actually to simplify this one first using power of a power law. So which means that's 3 to the a minus 7 is equal to 3. 3 times 2a is equal to 6a. And this implies that since we already have the same base 3, then therefore we can equate the exponent, and the exponents that we have are a minus 7 equal to 6a. And then using your skills in algebra, you can compute for the value of a. So that means negative 7 is equal to 6a minus a. Okay, using addition property of equality, and this will give you 5a equal to negative 7. And to solve for the value of a, we have to divide both sides by 5, giving us a equal to negative 7/5. So our solution here is a is equal to negative 7 over 5. Okay. Try to check the correctness of our solution by substituting the value of a into our original equation. Okay, let's try more problems. Okay, let's have this one. So as you can see, we have two different bases here, 5 and 3, and we have 75. Okay, the first and the best way to do this is actually to transform 75 into a negative exponent, because once you make this a negative exponent, you will observe that you will have 75 to the negative 1. Okay, remember the definition of your negative exponent. So if you want to transform a positive exponent to negative exponent, you find the reciprocal of the base. Now, 75 is our base and the exponent of 75 is 1. So when we use the definition of negative exponents, we can transform 75 to the negative 1 from 1 over 75. So because 75 is the reciprocal of 1 over 75. Now, observe this one. Remember, you can always use the loss of exponents vice versa or backwards. You can use that backwards. When I say backwards, look at this one. We have y here for the exponent of 5 to the 2y and 3, which means that we can rename this expression as 5 squared times 3 to the power of y. And we're using the power of a product law, which means that we have two different bases and we have the same y. Okay, with the same exponent. That is equal to 75 to the negative 1. And as you can observe, 5 squared times 3 is equal to 25 times 3, or just 75 to the power of y. That it will be 75 to the negative 1. And when you do that, you can get y equal to negative 1. Since you already have the same basis, then this implies that we can have y equal to negative 1. When you see this arrow, that means it implies, okay? We're not canceling out the basis here, but we're implying that since we have the same basis, then we can have the same, or we can equate the exponent. So therefore, the solution for this one is negative 1. Is there any alternative way to do this? Let's try to explore. This time, we're simplifying the expression 1 over 75 instead of these two. So that means we can copy this as 5 to the 2y times 3 to the y equal to 75 is still 75 to the negative 1. Okay? But you can actually transform 75 into 75 is 25 times 3 to the negative 1. And once you do that, you can have 5 to the 2y times 3 to the y is equal to 5 squared times 3 to the power of negative 1. Okay? As you can see, we already have 5 squared, 5 base 5 here, base 3 here, base 5 here, base 3 here. So that means we can also have 5 to the 2y times 3 to the y is equal to, you can distribute the negative exponent here, that will give you 5 to the negative 2, and this will be multiplied to 3 to the negative 1. Okay, this is power of a product law. Okay, so you can actually equate 5 to the 2y equal to 5 to the negative 2. Since you have the same basis now, then therefore 2y is equal to negative 2 and y is equal to negative 1. Just make sure that your value of y will still be consistent. Okay, now for this time, we have 3y, 3 to the y equal to 3 to the negative 1. And since we have the same basis 3 and 3, therefore it implies that we can equate the exponent y and negative 1. So therefore, y is still equal to negative 1. So therefore, when you get the same value of y here, then therefore your solution is correct. And our target answer for y is negative 1. Okay, I hope you understood that part. Okay, let's have this exercise. We have 1/3 to the power of negative z minus 1 plus square root of 3 to the power of 2z. The first thing that you're going to do is to actually transform everything into a base of a number, and that is not rational. So which means we have to transform everything in such a way that we can see bases in whole number. Okay, so in example with this one, I can rename this as 3 to the negative 1 to the power of negative z minus 1. This is using the definition of a negative exponent, plus we can transform this as 3 to the 1/2. This is the definition of radicals or fractional exponent equal to 6 squared. Okay, and that's the easiest number that we can think of. Now, based on this one, we can actually simplify this further. We can have 3 negative z times negative 1 is positive z. Negative 1 times negative 1 is positive 1. Plus 1 half times 2 is just 1. So that will be 3 to the z equal to 6 squared. Okay, now since all of these numbers cannot be expressed in same basis, but we can actually use product law of exponents to separate 3 to the z and 3 to the first power. Just remember, in product law, if you have the same basis, you're adding the exponent. So when you see expressions in the exponent with addends, that means you can separate them as in terms of their product. So that will be plus 3 to the z is equal to, and this one, we can actually use 2 times 3 here, quantity squared. Okay, and that will be the start of our solution. The next step that we're going to do is to actually factor out what is given here. So we can actually see that 3 to the z is common to terms, the first term and the second term. So we can take out 3 to the z, and when we take out 3 to the z, what happens? We will have 3 to the first, and that is plus 1. Or we can just erase the power 1 here. And we can distribute the 2 here, giving us 2 squared times 3 squared. 3 plus 1 is equal to 4. So basically, this is equal to 3 to the z times 4 equal to, this is 4 times 3 squared. What have you observed? We have 4 on this side and 4 on the other side, which means we can cancel out 4 here. Okay, so we divide both sides by 4. So that's multiplication property of equality. And since we have eliminated 4, then we can have 3 to the power of z equal to 3 squared. Okay, follow the solution. And therefore, since we have the same basis, then we can equate this implies that we can equate the exponent, giving you z equal to 2. Okay, I hope you understand that one. And let's try to explore some or other alternative way to solve this one.